Imagine standing on a ridge watching the world wake up for the first time in 50,000 years of ice. Below you, rivers carve fresh paths through valleys that have never known flowing water. Their currents carry the last memories of ice sheets that once pressed down like stone lids on the continent. Mastodons wade through marshlands still heavy with glacial melt. Their tusks catch sunlight that feels different somehow, warmer and kinder than anything their ancestors experienced during the endless winter that came before. The air carries scents that haven't existed for millennia. Wet earth mixing with new grass. The sweet decay of fallen logs in forests too young to have names. And something else, something indefinable that speaks of possibility rather than mere survival. This is Earth 14,700 years ago. Not the frozen wasteland our ancestors endured for generations, but something unprecedented, a world in the middle of remembering how to be alive. The transformation happened with breathtaking speed. Ice sheets that had crushed entire continents for tens of thousands of years began retreating northward. Behind them, they left landscapes that looked like rough sketches of paradise. What geologists call the Bølling Allerød period had begun. It brought the kind of climate stability that exists more often in dreams than geological reality. Temperatures rose sharply across the northern hemisphere. Winters shortened and summers stretched long and generous. The world painted itself green from horizon to horizon in ways that must have seemed impossible to people who had known only scarcity. For nearly 2,000 years, this golden window remained open. 2 millennia might seem brief when measured against geological time, but for humans living within it, this period represented something profound. It was the first extended stretch in countless generations when survival wasn't a daily gamble against cold and hunger. Children could grow up expecting abundance rather than famine. Communities could plant themselves like seeds in fertile ground. They could stay long enough to see what might grow from permanence rather than constant movement. Picture those first settlements if they existed at all. These wouldn't have been grand cities with towering walls and paved streets. Instead, something more tentative and experimental, clusters of substantial shelters built beside rivers that flowed year-round, food storage pits that could sustain communities through mild winters. Perhaps even the first careful experiments with cultivation, where wild grains began growing in neat, deliberately unnatural rows. The flourishing of human communities during this period is perhaps woven into myths that echoed in later texts. The Sumerians, the first writers of mankind, spoke of the era of Anu, the supreme sky god, who ruled over antediluvian kings whose impossibly long reigns were carefully documented in royal lists. Ancient Egypt itself preserved similar memories. They spoke of Zep Tepi, the first time when divine beings walked among humans. These entities established the foundations of knowledge and cosmic order that would guide all subsequent development. Egyptian chroniclers described actual beings who built the first temples, mapped star movements with precision, and taught the essential skills that separated organized civilization from chaos. Or the story of Atlantis, an incredibly sophisticated maritime civilization documented by the greatest philosopher of ancient Greece, Plato. Cities built from white and red stone, concentric canals that carried fresh water to every district. Engineering knowledge that allowed inhabitants to shape their environment on a scale that impressed even the monument-building Egyptians. When Plato wrote about Atlantis, he wasn't weaving fantasy for entertainment. He was struggling to explain something that didn't fit into the historical framework he understood, something that seemed to predate the civilizations he knew by an impossible margin. Many cultures separated by geography and centuries, preserved the same haunting motif. There had been before, a civilization age of knowledge and prosperity that ended abruptly and catastrophically. It left behind only fragments and whispers that later civilizations struggled to interpret. Modern archaeology adds unexpected weight to these persistent whispers, though not always in ways that support conventional timelines. Megalithic structures scattered around the world demonstrate mathematical principles that shouldn't have existed yet. Sophisticated tools appeared suddenly without clear developmental precursors. Astronomical alignments suggest systematic observation conducted over multiple generations. Each piece, examined individually, might yield conventional explanations that fit established models, but taken together they suggest something more intriguing. Human society might have achieved significantly more complexity during the Golden Window than current archaeology accepts as possible. The Bølling Allerød period provided exactly what such theoretical development would require: stable climate patterns that could be predicted from year to year, abundant resources that didn't require constant migration to access, predictable seasonal cycles that allowed for long-term planning, and perhaps most crucially, the luxury of time itself extending beyond immediate survival needs. This was time to experiment with new ways of organizing society, time to develop technologies that went beyond basic survival tools, time to accumulate and preserve knowledge across generations rather than losing it whenever experienced individuals died. Yet this temporal luxury contained within it a fatal limitation that nobody could have anticipated. After many millennia of stable climate, something fundamental changed. Temperatures plummeted across the northern hemisphere. Ice sheets advanced once again from their northern refugia. The easy, abundant world that had nurtured potential human development for 2,000 years suddenly changed. In its place came the harsh reality of what scientists now call the Younger Dryas, a return to glacial conditions. If early civilizations had indeed taken root during the warm period, this return would have been catastrophic beyond anything in recorded human experience. Complex social structures would have collapsed under the weight of simple survival necessity. The Golden Window would have closed forever, but it left behind questions that still glimmer in the archaeological record like frost patterns catching morning light. If humans did achieve something remarkable during those 2,000 years of stability, where did all evidence disappear? And if they didn't, if this was simply another phase in humanity's slow climb toward civilization, then why do independent cultures across the globe insist otherwise with such persistent unanimity? Perhaps the answer lies not in what survived the Younger Dryas catastrophe, but in what didn't survive. Not in the monuments that endured through 12 millennia of climatic chaos, but in the significance of absences that might speak more eloquently than surviving stone. The civilization age didn't fade gradually through natural decline. It was interrupted suddenly and completely by environmental forces that operated entirely beyond human control. And in that interruption, in that abrupt termination of possibility, might lie the key to understanding something profound about our own origins. The world we know today might not be humanity's first attempt at building something greater than mere survival. Tonight, we'll journey into the shadows of the Younger Dryas, a global apocalypse that turned the world upside down, erased what may have been ancient civilization, and reshaped the path of history. Stay with me as we uncover the hidden story behind the thousands-year winter. The wind that had carried warmth from the south suddenly turns bitter and sharp. Rivers that had run clear for centuries begin to freeze at their edges. The long summers that had become normal start shrinking, week by week, year by year. Campfires that once warmed families through mild winters now struggle against howling gales and endless snow. The world doesn't just grow cold, it gets yanked backward through time, returning to conditions that everyone assumed were buried forever in ancestral memory. Around 12,900 years ago, Earth entered what scientists call the Younger Dryas period. The name comes from a small Arctic flower that suddenly appears in sediment layers where it had no business being. Within just a few decades, temperatures across the northern hemisphere plummeted between 7 and 10 degrees Celsius. To put that in perspective, it would be like New York suddenly developing the climate of northern Canada and staying that way for over 1,000 years. This wasn't a gradual decline into winter. It was what researchers describe as a system break, a violent disruption in the planet's climate machinery that happened faster than anything in the geological record. But here's where the mystery deepens. The Younger Dryas didn't happen everywhere at once. In northern Europe, the transition to cold conditions occurred within 10 to 20 years. People who had spent their youth in a warming world suddenly found themselves struggling through winters that lasted 8 months. Eastern Europe plunged into harsh, dry conditions almost immediately, but the Iberian Peninsula experienced a strange, intermediate phase. Several centuries of warm, dry weather before finally shifting to the cold, wet conditions that characterized the period elsewhere. The timing varied in puzzling ways even within the same continent. North America became the second most affected region after Europe. In the northeast United States, winter temperatures dropped by roughly 7.5 degrees Celsius. Summers turned cool and dry. The massive forests that had grown during the warm period couldn't survive the new conditions. They died back, replaced by tundra that stretched from horizon to horizon like a grey-green carpet of survival. The Laurentide ice sheet, a massive glacier that once covered most of North America, which had been steadily shrinking for thousands of years, suddenly reversed course and began advancing south again. Across the Great Plains, blizzards became a regular feature of life. The easy world of the golden window had slammed shut, leaving behind something that looked disturbingly like the Ice Age their grandparents had described in stories. In East Asia, however, the cold took centuries to arrive. Lake sediments in Japan show that temperatures didn't drop significantly until about 600 years after Europe had already frozen solid. This asynchronous pattern suggests something more complex than a simple global cooling event. The Younger Dryas behaved like a climate contagion, spreading from region to region through mechanisms that remain poorly understood. Meanwhile, the rest of the planet seemed to exist in a different reality, but different didn't mean better. The southern hemisphere avoided the crushing ice sheets, but it faced its own version of chaos. In the Andes, ancient lake sediments tell a story of sudden drought and ecological collapse. Black layers rich with charcoal appear in the geological record around 12,800 years ago, evidence of massive wildfires that swept across landscapes already stressed by changing rainfall patterns. Lakes like Victoria and Tanganyika in East Africa dropped to critically low levels. Grasslands spread across cracked, drying earth as reliable water sources became seasonal or disappeared entirely. The climate didn't just become harsher, it became unpredictable, forcing human populations to abandon territories that had supported them for generations. Australia presents the most complex picture of all. While the continent did become wetter and warmer in some regions, this apparent improvement masked deeper instabilities. The abnormal rainfall patterns disrupted ecosystems that had adapted to Australia's traditionally arid conditions. Species that had thrived in dry environments suddenly found themselves at a disadvantage, while others exploded in population, creating new imbalances that rippled through entire food webs. This geographic complexity makes the Younger Dryas far more disturbing than a simple return to Ice Age conditions. It wasn't a global cooling event that affected everyone equally. Instead, it was as if someone had rewired the planet's entire climate system, creating a patchwork of different disasters tailored to each region's vulnerabilities. The biological consequences were catastrophic and highly specific. In Europe, pollen records from sites like Meerfelder Maar in Germany show the complete disappearance of temperate tree species within decades. Oak, elm, and hazel trees that had dominated the landscape for nearly 2,000 years vanished from the fossil record, replaced by hardy shrubs and grasses that could survive the new Arctic conditions. North American forests experienced similar devastation. Spruce trees that had formed vast boreal forests during the warm period died off in massive numbers, creating what paleobotanists call forest cemeteries, landscapes littered with fallen timber that wouldn't decay in the new permafrost conditions. These dead forests are still visible in sediment cores as distinct layers of woody debris sandwiched between normal organic deposits. But it was the collapse of megafauna populations that created the most visible evidence of ecosystem breakdown. The Younger Dryas coincided with one of the most dramatic extinction events in recent geological history, eliminating roughly 80% of large mammal species in North America and significant numbers elsewhere. The woolly mammoths provide perhaps the most haunting example. These giants had survived countless climate fluctuations for hundreds of thousands of years, adapting to ice ages and warm periods with equal success. Their final populations on the mainland disappeared around 12,800 years ago, just as the Younger Dryas was reaching peak intensity. Archaeological sites across Siberia and North America show mammoth bones from this period bearing signs of stress and malnutrition, evidence of creatures struggling against environmental changes they couldn't escape. But it wasn't just the cold-adapted species that suffered. Saber-toothed cats, which had been apex predators for over 1 million years, left no descendants. Ground sloths the size of modern elephants, giant beavers as large as bears, American horses and camels, an entire bestiary of Ice Age giants disappeared as if someone had simply erased them from existence. However, the most profound collapse may have been happening in human communities before the Younger Dryas began. As it happened, these nascent civilizations faced a crisis unlike anything in recorded history. For over 1,000 years, they remained locked in conditions that tested the limits of human endurance. Winters stretched longer, while summers shrank, causing frequent frosts that rendered much of the land unsuitable for cultivation or permanent settlement. Global rainfall patterns shifted beyond recognition. Regions that had known reliable precipitation for millennia suddenly faced prolonged droughts that cracked the earth and dried up water sources. Other areas found themselves battered by unpredictable floods and violent weather systems that made planning impossible. Ecosystems transformed with devastating speed. Ancient forests withered and died, replaced by cold grasslands that supported fewer species and provided less shelter. Rivers that had flowed for thousands of years froze solid for months at a time or dwindled to mere streams. The landscapes that humans had learned to navigate and depend upon became unrecognizable. Familiar landmarks disappeared beneath advancing ice. Migration routes that animals had followed for generations were blocked or abandoned. The reliable seasonal patterns for millennia were replaced by chaos. Even the hardiest grains and most adaptable animals struggled to survive in these altered conditions. Food sources that had sustained communities for centuries became unreliable or vanished entirely. Storage systems that had worked for generations proved inadequate against winters that refused to end and summers that failed to deliver. No matter how advanced or well organized, No human society could withstand such relentless environmental pressure indefinitely. What had taken centuries to build was slowly dismantled by the simple necessity of survival, as communities were forced to abandon sophisticated practices and return to the most basic strategies for staying alive. Perhaps most tragically, the knowledge preservation systems these societies had developed over centuries would have been among the first things lost. Whatever methods they had used to record astronomical observations, preserve technical knowledge, or maintain cultural traditions would have been abandoned as oral history reverted to the more immediate concerns of survival. Entire generations were born, lived, and died, knowing only the harsh reality of the Younger Dryas world. By the time 13 centuries had passed, cultural memory of the warm period would have faded into the realm of legend. Stories of abundance, of permanent dwellings, of a time when the earth provided plenty without constant struggle. These would have become mythical tales passed down by survivors who might not have fully understood what they were preserving. Whatever human civilization had achieved during the golden window had endured over a millennium of climatic chaos. Most of it hadn't survived intact, might only be preserved in megalithic structures scattered around the world. To investigate the causes of the beginning of the Younger Dryas, geologists began searching the Earth itself for clues. They found their evidence in the geological record of one of Europe's most catastrophic eruptions. That morning, the lake surface lay mirror-still beneath a peaceful European sky. Then the Earth cracked open with a sound that shattered the silence of millennia. The explosion of Holocene sent ash columns 40 kilometers into the stratosphere, transforming the sun into a pale, ghostly disk hanging in a sulfur-yellow sky. Within hours, a fine grey powder began falling like deadly snow across landscapes that had never known such darkness. The volcano, which had slept quietly beneath green hills for thousands of years in Germany, spoke in the only language it knew: fire, ash, and poison gas. When the mountain opened, it released more than just molten rock and debris. Millions of tons of sulfur dioxide rose into the stratosphere, creating a thin veil that reflected sunlight back into space. The atmosphere gained an unwanted filter. Light still penetrated enough for people to see each other, but not enough to warm the earth. It was summer with a sun that gave no summer. The first rains after the eruption carried the metallic taste of acid. Leaves developed brown spots where the poisoned water touched them. Wells filled with water that reeked of sulfur. People wrapped cloth around their faces, but the fine ash found its way into everything. Eyes, throats, stored grain, carefully crafted tools. The grey powder covered rooftops mixed with mud to create treacherous walking surfaces and drifted through every crack and crevice of human shelter. Communities that had flourished during the warm centuries suddenly faced impossible choices. Do you stay in a familiar place that can no longer support life, or venture into an ash-covered landscape where every familiar landmark has been transformed? But the immediate impact was only the beginning of the story. The ashfall extended far beyond the immediate blast zone. Hundreds of miles from the eruption, skies darkened and temperatures dropped. Insects died and fell into streams. Fish floated belly up in rivers as the water chemistry changed. Animal herds that had followed the same migration routes for generations abandoned their traditional paths, sensing something fundamentally wrong with the world. Plant communities that had barely recovered from previous cold periods now faced a double assault. The ash physically blocked the breathing pores on leaves while the acid rain burned whatever vegetation it touched. Tree ring analysis from across Europe shows growth patterns that tell the story clearly. Rings that suddenly narrow, trees that stop growing entirely, forests that began dying from the inside out. For people living within several hundred miles of the eruption, survival became a daily challenge that would have tested even the most adaptable communities. The ash had to be swept from shelter roofs constantly to prevent collapse. Water sources required careful filtration. Hunting became nearly impossible when animal populations fled or died. The techniques that had sustained communities for generations suddenly became useless against conditions no living person had experienced. Modern science can read this ancient disaster in precise detail. The Lac-Sea ash layer appears in lake sediments throughout the Rhineland like a geological signature dated to exactly the period when Greenland ice cores show the dramatic temperature drop that marked the beginning of the Younger Dryas. The sulfur spikes in those same ice cores confirm that volcanic gases reached the global atmosphere and affected climate worldwide. The timing is too perfect to ignore. Just as the golden window was closing and the 1,000-year winter was beginning, one of the most powerful volcanic eruptions in European prehistory sent enough debris into the atmosphere to dim the sun across an entire continent. The coincidence seems to solve the mystery that had puzzled researchers for decades. Yet even as the evidence mounts, questions begin to emerge that complicate this apparently straightforward explanation. Volcanic winters, however dramatic, typically last only a few years. The ash settles out of the atmosphere within months, and sulfur compounds wash out within a decade at most. Mount Tambora, the volcanic eruption that caused the year without a summer in 1816, affected global climate for less than 3 years. Even the massive Toba eruption 74,000 years ago, which may have brought humanity close to extinction, caused a volcanic winter that lasted only a few decades. But the Younger Dryas persisted for over 13 centuries. That's not just longer than typical volcanic effects, it's nearly 50 times longer than the most extreme volcanic winter on record. The mathematics of atmospheric chemistry simply don't support the idea that even the most massive eruption could maintain global cooling for more than a millennium. This timing discrepancy has led some researchers to propose that the Lac-Sea eruption might have been a trigger rather than a cause. Perhaps the volcanic cooling was just severe enough to tip an already unstable climate system over the edge into a different state. The eruption provided the initial shock, but other mechanisms, ocean circulation changes, ice sheet dynamics, atmospheric feedback loops, sustained the altered climate long after the volcanic effects should have faded. This interpretation makes the eruption even more significant, not less. If the climate system was balanced so precariously that a single volcanic eruption could trigger a 1,000-year shift, then the golden window before the Younger Dryas was more fragile than anyone had imagined. The sophisticated communities that had developed during those 2 millennia of stability were living on borrowed time, entirely unaware that their world could be destroyed by forces completely beyond their control or prediction. For the survivors of the Lac-Sea eruption, the immediate crisis would have overshadowed any concerns about long-term climate effects. The first priority was simply breathing clean air and finding uncontaminated water. The second was locating food in a landscape where most plants and animals had either died or fled. The third was deciding whether to wait for conditions to improve or abandon everything they had built and search for refuge elsewhere. Archaeological evidence suggests that many communities chose abandonment. Settlement sites across Central Europe show breaks in occupation dating to exactly this period. It's as if entire cultures had been forced to compress their accumulated knowledge down to whatever could be carried by desperate refugees. Even more tragically, the recovery from volcanic devastation would have been slow and incomplete. The soils that had been poisoned by acid rain would have taken decades to restore their fertility. The forests that had been killed by ashfall would have required centuries to regrow. The animal populations that had fled the devastation might never have returned to their traditional ranges. By the time the immediate effects of the eruption had faded, the communities that might have preserved the achievements of the Golden Window would have been scattered across the landscape, carrying only fragments of their former knowledge. The volcanic winter had not just interrupted their development, it had reset their entire civilization back to a survival baseline. Even as the ash cleared and the sulfur clouds dissipated, the cold remained. The sun emerged from its haze, but the warming didn't follow. Rivers that should have flowed freely remained frozen. Growing seasons that should have lengthened stayed short and unpredictable. The volcanic trigger had been released, but the 1,000-year winter continued without it. Something else had taken over the role of maintaining the altered climate, something that operated on time scales and geographic scales that dwarf even the most massive volcanic eruption. The Lusher sea blast may have been the event that started the Younger Dryas, but it was not the force that sustained it through 13 centuries of relentless cold. This realization shifts the volcano from being the solution to the mystery into being merely its first chapter. The explosion that darkened the sky was dramatic enough to serve as a trigger, but not powerful enough to explain what followed. Something else was required to keep the world locked in winter for over a millennium. Something that makes volcanic eruptions seem small by comparison. The volcano pulled the trigger, but what had loaded the gun might have come from the stars themselves. Some researchers began looking beyond our planet's surface entirely, toward the vast darkness above, where objects moving at cosmic speeds could turn continents to dust and transform civilizations into myths. A streak of light tears across the sky. Blazing fragments rain down like fallen stars, turning night into day and forests into seas of flame. This vision, whether real or imagined, has haunted humanity since our earliest stories began. It offers the most dramatic possible explanation for catastrophe, destruction that comes not from the earth below or the oceans beside us, but from the infinite void above. The idea that cosmic impacts might have triggered the Younger Dryas first gained serious scientific attention in 2007, when a team of researchers led by Richard Firestone and Alan West proposed a startling hypothesis. They argued that the abrupt climate change hadn't been caused by terrestrial forces at all, but by a comet or cluster of asteroids exploding in Earth's atmosphere around 12,800 years ago. The impact hypothesis offered elegant simplicity, a single dramatic event that could explain not just the climate catastrophe, but also the mysterious extinction of North American megafauna and the apparent collapse of the Clovis culture. It was cosmic catastrophe as the ultimate explanation, sudden, decisive, and capable of resetting entire continents. But it was through the work of Graham Hancock that this scientific hypothesis reached popular audiences and gained its most detailed narrative form. In books such as America Before and the Netflix series Ancient Apocalypse, Hancock transformed the impact theory into a comprehensive story of cosmic destruction that captured imaginations worldwide. According to his interpretation, the destruction began not with a single asteroid strike, but with a massive comet that had entered the solar system on an Earth-crossing orbit around 20,000 years ago. This comet eventually fragmented, creating a debris stream that would intersect with our planet's path twice in the following millennia. The first wave of fragments struck around 12,800 years ago, triggering the onset of the Younger Dryas. The second bombardment occurred around 11,600 years ago, coinciding with the end of the Ice Age period. The remnants of this ancient comet, Hancock argued, still exist today in the Taurid meteor stream and comet Encke, creating an ongoing threat that cycles through Earth's vicinity every few thousand years. The mechanism of destruction, as Hancock describes it, was unlike the single massive crater that ended the age of dinosaurs. Instead, it was a shotgun blast of multiple fragments that created airbursts across the northern hemisphere, or struck the surface in a scattered bombardment pattern. Some of the larger fragments, he suggested, impacted directly on the ice caps of North America and northern Europe, causing catastrophic melting that generated what he called superfloods across entire continents. In Hancock's vivid reconstruction, the immediate aftermath resembled a nuclear winter that persisted far longer than typical impact events. The combination of atmospheric debris, massive wildfires triggered by the airbursts, and the sudden disruption of ice sheets created a feedback loop that maintained frigid conditions for over 13 centuries. Fragments striking the ice caps caused sudden, massive melting that not only carved new geological features, but also dumped enormous quantities of fresh water into the oceans, potentially disrupting global circulation patterns and locking the planet into its altered climate state. These cosmic airbursts triggered massive wildfires across North America, leaving behind a distinctive layer of carbon-rich sediment called black mats that could be found at dozens of archaeological sites. He connected them to the simultaneous extinction of North American megafauna and the collapse of the Clovis culture. The impact created continent-wide conflagrations that consumed entire ecosystems, eliminating both the large animals that had survived the Ice Age and the human cultures that depended on them. This dramatic narrative found a receptive audience among the general public. The evidence supporting cosmic impact was intriguing. Some research groups reported finding the telltale markers of extraterrestrial collision, tiny glass spherules that form only under extreme heat, microscopic diamonds that require enormous pressure to create, and unusual concentrations of rare elements like platinum and iridium that are common in asteroids but rare on Earth's surface. These materials appeared at sites across North America and in some locations in South America and Greenland, all dating to the crucial period around 12,800 years ago. The geographic distribution seemed to support the idea of multiple impacts or airbursts across a wide area, just as Hancock and the original researchers had proposed. The hypothesis lingered in scientific controversy for nearly 2 decades, dismissed by many mainstream researchers. They argued that the black mats were simply evidence of natural wildfires that had occurred during the climate transition, not cosmic impacts. The microscopic spherules could have formed in ordinary volcanic activity. The rare elements might have come from terrestrial sources rather than extraterrestrial ones. Most critically, despite decades of searching, no one had found craters of appropriate size and age to match the proposed impact events. On August 6, 2025, a study published in PLOS 1 provided the most compelling evidence yet for cosmic impact at the Younger Dryas boundary. Christopher R. Moore and his colleagues had drilled sediment cores from Baffin Bay, between Greenland and Canada, extracting material from layers dated to exactly 12,800 years ago. What they discovered in the deep ocean sediments offered independent confirmation of the impact hypothesis from a completely different environment. The cores contained iron-rich silica spherules that form only at the extreme temperatures generated by meteorite impacts. The researchers also found metallic debris with chemical compositions matching known comet dust, along with unusual concentrations of platinum, iridium, and nickel, elements that are rare on Earth's surface but common in extraterrestrial objects. For the first time, evidence from the ocean depths matched the terrestrial findings that had sparked decades of controversy. The Baffin Bay discovery suggested that Hancock's general scenario might have been correct in its broad outlines. Multiple cosmic impacts or airbursts had indeed occurred around 12,800 years ago, spreading debris across both land and sea. The evidence supported the idea of a fragmented comet or asteroid swarm rather than a single impact event. Yet even this theory couldn't resolve the fundamental problem, the question of duration. Cosmic impacts, regardless of their size or number, typically affect climate for only a few years or decades at most. Even the asteroid that killed the dinosaurs 66 million years ago created an impact winter that lasted less than a century. The debris settles out of the atmosphere, the smoke clears, and normal climate patterns resume relatively quickly. But the Younger Dryas persisted for over 13 centuries, far longer than any known impact effects could maintain. Hancock's scenario of a prolonged nuclear winter lasting 1,300 years contradicted everything scientists understood about atmospheric physics and climate recovery. No amount of debris or smoke could remain in the atmosphere long enough to block sunlight for more than a few years. The mathematics simply didn't support the idea that even multiple impacts could directly maintain global cooling for over a millennium. This timing discrepancy didn't necessarily invalidate the evidence for cosmic impact, but it suggested that the true story was more complex than either the original scientific hypothesis or Hancock's popular narrative had proposed. If cosmic impacts really had occurred at the beginning of the Younger Dryas, they could explain the dramatic onset of cooling, but not its extraordinary persistence. The impacts might have served as triggers rather than direct causes, the first dominoes in a cascade of environmental changes that fed off each other in devastating sequence. Perhaps the cosmic bombardment weakened ice dams that were already under stress from millennia of warming. Perhaps the wildfires and atmospheric disruption provided the final push that caused volcanic systems like Holocene to erupt. Standing beneath a clear night sky, watching the peaceful dance of stars that has continued unchanged throughout human memory, it becomes difficult to imagine that this serene darkness once harbored fragments of destruction. But the evidence suggests that our ancestors may have witnessed something far more dramatic than anything recorded in historical memory, a light show that marked the end of their world and the beginning of humanity's longest winter. Whether that light came from a comet, as Hancock believes, or from some other source entirely, its legacy may still be written in the deepest human memories of disaster and recovery, loss and renewal. The comet that never was, or perhaps the comet that was, reminds us that the difference between cosmic accident and civilizational catastrophe may be nothing more than a question of timing, trajectory, and the fragile systems that keep our world habitable. To further investigate the causes of the Younger Dryas's prolongation, scientists turned their attention to the ocean itself, searching for forces powerful enough to sustain a 1,000-year winter. They discovered their answer in the Atlantic Ocean, a massive heart beating in slow motion across geological time. Each pulse beneath sends warm water flowing northward from the equator, carrying tropical heat toward Europe and the Arctic. Warm, salty water from the tropics flows north, where it cools and becomes dense enough to sink. This sinking action pulls more warm water northward, maintaining the circulation. This system, the Atlantic Meridional Overturning Circulation, or AMOC, creates a conveyor belt of circulation that has regulated Earth's climate with steady reliability for millions of years. But what if the heart stopped beating? According to many researchers, within decades, a circulation system that had remained stable through countless climate variations simply shut down, plunging the Northern Hemisphere into a 1,000-year winter, while paradoxically warming much of the Southern Hemisphere. The mechanism behind this catastrophe lies in one of the most dramatic flood events in Earth's recent history. During the golden window before the Younger Dryas, massive ice sheets across North America had been steadily melting for thousands of years. This meltwater didn't simply flow directly into the ocean, much of it collected behind natural ice dams, forming glacial lakes of unprecedented size. The largest of these was Lake Agassiz, a body of water that covered an area nearly the size of the modern Caspian Sea. Lake Agassiz held more fresh water than all the Great Lakes combined. For centuries, this enormous reservoir remained trapped behind walls of ice that seemed as permanent as mountains. The lake expanded and contracted with seasonal changes, but the fundamental barrier held. Indigenous peoples living around its shores would have known it as an inland sea that stretched beyond the horizon, a permanent feature of their world. But ice dams, no matter how massive, are fundamentally unstable structures. As the climate continued warming during the late stages of the Golden Window, the ice walls containing Lake Agassiz began to weaken. Cracks appeared, seepage increased. The dam that had held back cubic miles of fresh water for millennia was approaching its breaking point. When the collapse finally came, it happened with devastating speed. Geological evidence suggests that the ice dam failed catastrophically, releasing the entire contents of Lake Agassiz into the North Atlantic in a matter of months or possibly even weeks. The flood was so massive that it would have temporarily raised global sea levels by several meters. But the real damage wasn't from the flood itself, it was from what that enormous pulse of fresh water did to the ocean's circulation system. The Lake Agassiz flood dumped millions of cubic miles of fresh water directly into the North Atlantic. Fresh water is less dense than salt water, and this massive influx created a layer of relatively light water floating on the ocean's surface. The warm water from the south could no longer penetrate this freshwater barrier, so it could not evaporate and become heavy enough to sink deep into the ocean. No sinking meant no suction, which led to no warm water flowing north. The whole heating system for Europe and North America simply stopped working. The evidence for this catastrophic shutdown is preserved in ice cores from Greenland, which show temperature drops of 7 to 10 degrees Celsius occurring within just a few decades. Marine sediment cores from the North Atlantic tell the same story through changes in the microscopic organisms that lived in the water. Species that thrived in warm surface waters suddenly disappeared, replaced by cold water organisms that indicate a dramatic shift in ocean conditions. Sea level records from this period add another piece to the puzzle. When the AMOC shut down and temperatures plummeted, ice sheets began advancing again across North America and Europe. This locked up enormous quantities of water, causing global sea levels to drop by 20 to 40 meters. The geographic pattern of the Younger Dryas makes perfect sense when viewed through the lens of AMOC collapse. The regions that experienced the most severe cooling, Northern Europe and Eastern North America, were exactly those that had depended most heavily on heat transported by the Atlantic circulation. When that heat source disappeared, these areas reverted to the harsh conditions they would have experienced based on their latitude alone. Meanwhile, the Southern Hemisphere experienced warming during the same period. This apparent paradox actually supports the AMOC hypothesis. When the circulation system shut down, the heat that would normally have been transported north remained in tropical and southern regions. The energy didn't disappear, it was simply redistributed, creating a climate seesaw effect that lasted for centuries. But perhaps the most unsettling aspect of the AMOC hypothesis is what it reveals about the vulnerability of Earth's climate system. A single lake, when released from its icy constraints, was sufficient to paralyze a circulation system that had remained stable through millions of years of gradual climate change. One regional flood event triggered over a millennium of global climate chaos. For over 13 centuries, the Atlantic remained in this altered state. The warm water that should have flowed north stayed trapped in southern latitudes. The ocean that had once been Earth's primary heat distribution system became a barrier to climate recovery. Ice sheets that had been retreating for thousands of years reversed course and began their advance southward, locking up enough water to lower global sea levels by dozens of meters. Then, around 11,550 years ago, something changed. The AMOC switched back on with the same dramatic speed that had characterized its shutdown. Temperatures shot back up across the northern hemisphere. Ice sheets began their final retreat. The ocean resumed its ancient role as a planetary thermostat, and the climate returned to the warming trajectory it had been following before the Great Interruption. The AMOC hypothesis provides the most scientifically robust explanation for the Younger Dryas that has been proposed to date. It accounts for the rapid onset, the geographic distribution of effects, the duration of the event, and the equally rapid recovery that marked its end. The mechanism is well understood, the evidence is strong, and similar events have been documented at other points in Earth's climate history. Yet one troubling question remains unanswered. Computer models suggest that the AMOC should recover from a freshwater shutdown within a century or two at most. The circulation system, once the disturbing fresh water disperses, should naturally restore itself as the ocean's salinity returns to normal levels. But the Younger Dryas lasted for over a millennium, nearly 10 times longer than the models predict. The answer may lie in the peculiar nature of the AMOC itself. This circulation does not simply switch on and off, it has two stable modes. In its strong state, salty waters sink in the North Atlantic, pulling warm currents northward. In its weak state, once fresh water has thinned the salinity enough, the sinking stops and the system can remain trapped there for centuries, a climate machine stalled by its own inertia. Into this fragile balance poured not one flood, but many. As the Laurentide ice sheet melted, Lake Agassiz and other glacial lakes repeatedly burst their icy dams. Each pulse of fresh water struck the AMOC just as it might have begun to recover, reinforcing the collapse again and again. Feedbacks in the climate then deepened the trap. With circulation weakened, the northern hemisphere cooled, snow and ice spread, and Earth's surface reflected more sunlight back into space. Cold oceans evaporated less, reducing salinity further. These loops conspired to hold the system in its weakened mode long after the first floodwaters were gone. Ultimately, the Younger Dryas, whatever its cause, left behind thousands of years of silence, a blank corridor in history where answers should be. It is as if time itself paused, holding the world in suspension, while something unseen pressed its hand against the scales of climate. And one haunting question lingers still: how far might human civilization have advanced had it not been forced to survive a gauntlet of apocalyptic winters? After more than 1,000 years of relentless winter, the massive ice walls that had imprisoned entire continents began to crack. The Laurentide ice sheet, which had stretched across North America like a frozen fortress, developed deep fissures that spiderwebbed across its surface. In northern Europe, the Fennoscandian ice sheet groaned under its own immense weight as warming air carved channels through ice that had remained solid for over a millennium. These weren't the gradual melts that had characterized previous climate transitions. They were structural collapses on a continental scale. Water began flowing from every crevice and crack. What started as tiny streams became torrents, then glacial rivers that thundered toward the sea with the force of geological vengeance. The ice that had locked up enough water to drop global sea levels by 40 meters was returning to the oceans all at once, transforming Earth's coastlines in the process. Around 11,550 years ago, the Younger Dryas ended as abruptly as it had begun. Global temperatures shot upward within decades. Ice sheets that had advanced steadily for over a millennium suddenly reversed their march, and warm winds began flowing northward from regions that had been climatically isolated for centuries. The 1,000-year winter was over, but its end brought catastrophes of its own. Scientists call it meltwater pulse, 1b, a surge of sea level rise that ranks among the most dramatic in Earth's recent geological history. Evidence from coral reefs in Barbados and coastal sediments around the world shows that global sea levels rose 14 to 18 meters in just 2 to 3 centuries. That translates to roughly half a meter per decade, more than 10 times faster than the current rate of sea level rise. To understand the human impact of such rapid change, picture a coastal village where generations of people had lived by fishing and gathering marine resources. Within the lifetime of a single individual, the sea would advance inland by several miles. Familiar landmarks, the distinctive boulder that marked fishing grounds, the ancient tree that served as a navigation point, would disappear beneath the waves year by year. Entire coastal plains that had supported communities for millennia simply vanished beneath the advancing ocean. This wasn't a regional event affecting only certain areas. The meltwater pulse was a global phenomenon that redrew the world's coastlines permanently. River deltas that had built up over thousands of years were submerged. The network of migration routes, resource areas, and seasonal settlements that had sustained human populations was shattered in the space of a few centuries. If sophisticated settlements had indeed developed during the golden window before the Younger Dryas along the world's coastlines, then many of these pioneering efforts now lie beneath the modern continental shelf, beyond the reach of conventional archaeology. This interpretation gives new meaning to some of humanity's most persistent myths and legends. Plato's account of Atlantis describes a prosperous civilization that vanished beneath the sea in a single night of catastrophe. Could the Atlantis story be a garbled but genuine memory of coastal communities that were actually swallowed by the rising seas at the end of the Younger Dryas? The timing aligns remarkably well. Plato claimed that Atlantis disappeared around 11,600 years ago, within decades of when meltwater pulse 1b occurred. Nor are flood stories unique to Greek civilization. In every corner of the world, people remember the day the water came. The Epic of Gilgamesh tells of a great deluge that destroyed the world, forcing survivors to build an ark to preserve humanity and animal life. Hindu traditions speak of cosmic floods that periodically cleanse the earth and force civilization to begin anew. Native American cultures across both North and South America preserve stories of great waters that rose suddenly, forcing their ancestors to flee to higher ground and abandon their traditional homelands. These flood narratives appear in cultures separated by vast distances and thousands of years of independent development. Walk into any university anthropology department and ask about flood myths, and you'll receive a patient explanation that has satisfied scholars for over a century. These stories, you'll be told, are natural products of the human condition, psychological artifacts born from our universal relationship with water and our collective need to process disaster. The reasoning seems solid enough. Every early civilization developed near rivers because water meant life, but rivers also brought death in the form of seasonal flooding. When the Nile overflowed or the Tigris burst its banks, entire communities could be wiped away in a matter of hours. The survivors, traumatized by the sudden transformation of their familiar world into an alien waterscape, would naturally tell stories about divine judgment and moral cleansing. Over generations, these local disaster tales would grow in the telling, becoming cosmic rather than regional, mythological rather than historical. Anthropologists call this convergent myth-making, the tendency for similar stories to emerge independently in response to similar experiences. Flooding is traumatic everywhere, so flood stories develop everywhere. The boat represents survival, the animals represent hope, The rainbow represents renewal. These are universal human symbols responding to universal human experiences, not evidence of shared historical events. Furthermore, the similarities between cultures can be explained by what scholars term diffusion theory. Stories travel along trade routes carried by merchants, migrants, and missionaries. The flood narrative could have originated in one location, most likely ancient Mesopotamia, where some of the earliest written versions appear, and then spread across the globe through the vast networks of human contact that connected even the most distant civilizations. Recent genetic and archaeological evidence reveals that human populations mixed and migrated far more extensively than previously thought, creating invisible highways along which powerful stories could travel for thousands of years. This academic framework held comfortably for decades. Flood myths were filed away as interesting examples of how human psychology processes trauma, useful for understanding cultural development but irrelevant to actual history. The matter seemed settled. Then researchers began to count, and the counting revealed something that didn't fit the comfortable explanations. When Sir James Frazer compiled flood stories for his comprehensive study Folklore in the Old Testament in the early 1900s, he documented versions from over 200 cultures across 6 continents. What struck him wasn't just the number of stories, it was their structural similarity. These weren't loose variations on a theme, but narratives that followed the same precise sequence: divine warning, chosen survivor, vessel construction, animal preservation, global destruction, gradual recession, new beginning. This isn't coincidence. It's too precise, too structured, too universal to be random cultural invention. The flood in these stories doesn't merely destroy, it selects what deserves to survive and what should be forgotten. And what survives isn't random. It's always the fundamental building blocks of civilization: how to grow food, how to organize society, how to maintain relationships with the divine, how to begin again when everything familiar has been swept away. This suggests that these myths serve a deeper function than simple storytelling. They're templates for survival, cultural instruction manuals disguised as religious narratives. If a catastrophe really did occur, one that wiped out coastal settlements and displaced populations across the globe, then physical monuments would be destroyed, written records would be lost, and sophisticated technologies would vanish. But stories can survive anything. They move from mouth to mouth, from parent to child, carried like seeds across time and distance. They can cross language barriers, adapt to new cultures, and preserve essential information even when the original context has been completely forgotten. And over generations, the trauma of real events can transform into the rhythm of myth: the warning, the preparation, the catastrophe, the loss, the survival, the renewal. The archaeological challenge is that evidence for pre-Younger Dryas coastal settlements now lies beneath hundreds of feet of ocean water. Traditional land-based archaeology cannot reach these submerged landscapes without enormous technical effort and expense. This absence of evidence shouldn't be interpreted as evidence of absence. It might simply reflect the fact that we're looking for traces of early civilization in places that are no longer accessible. Modern climate science provides a clear mechanism for the rapid end of the Younger Dryas and the subsequent meltwater pulse. The Atlantic circulation system that had been disrupted by the initial freshwater flooding gradually recovered as the interfering water masses dispersed. Once the circulation resumed, it began transporting tropical heat northward again with renewed efficiency. Simultaneously, Earth entered a favorable phase of its orbital cycles, receiving increased solar radiation in the northern hemisphere. These two mechanisms working together, oceanic and astronomical, created a powerful feedback effect that accelerated warming beyond what either factor could have achieved alone. The recovery from the Younger Dryas wasn't gradual but explosive, causing ice sheets to collapse and sea levels to rise at rates that have few parallels in the geological record. For the human survivors of the 1,000-year winter, this dramatic transformation must have seemed like the end of the world all over again. They had endured over a millennium of harsh conditions, learned to survive in a climate that was colder and more challenging than anything in recorded human experience, and developed the social structures necessary to maintain their communities through centuries of environmental stress. Just as they might have been establishing a new equilibrium with their transformed world, the ice collapsed and the seas rose to swallow much of what they had built. Coastal communities that had relocated to lower elevations during the long period of reduced sea levels suddenly found themselves facing an advancing ocean that showed no signs of stopping. The displacement would have been enormous. Entire populations would have been forced to move inland, carrying only what they could transport quickly. The river valleys, coastal plains, and island settlements that had become home during the cold period were abandoned to the rising waters. Generations of accumulated knowledge about local resources, seasonal patterns, and navigation routes became obsolete overnight. Yet this catastrophic ending also marked a new beginning. The same warming that caused the meltwater pulse also made vast areas of previously frozen landscape habitable for the first time in over a millennium. As the ice retreated, it revealed fertile valleys, navigable rivers, and resource-rich territories that had been locked beneath glaciers throughout the Younger Dryas period. The survivors, who had been displaced from their coastal homes, found themselves in a world of unprecedented opportunity. The harsh selection pressures of the 1,000-year winter had produced human populations with the skills, social organization, and accumulated knowledge necessary to rapidly colonize and develop these newly available territories. This combination of displacement and opportunity might explain one of the most puzzling features of early post-glacial human development: the extraordinary speed with which complex societies emerged once the ice retreated. The rapid development of agriculture, the sudden appearance of monumental architecture, and the sophisticated astronomical knowledge evident in early temples and stone circles all suggest that humans weren't discovering these capabilities for the first time, but were applying knowledge and techniques that had been preserved and refined during the long winter. The rising waters that destroyed the coastal settlements of the late Younger Dryas also carried the seeds of what would become historical civilization. The refugees from the drowned landscapes brought with them whatever knowledge, techniques, and social structures they had managed to preserve through the long winter. Forced into new territories by rising seas, they became the founders of the agricultural and urban societies that would ultimately give rise to recorded history. The silence beneath the waves, where ancient coastlines once supported human communities, is not just geological testimony to climate change. It might be the physical grave of humanity's first experiments with complex society. But graves, as any archaeologist knows, also preserve treasures. The rising waters that ended one chapter of human development also began another, setting the stage for everything that would follow. Deep beneath the modern ocean, beyond the reach of conventional exploration, lie the drowned landscapes of our forgotten past. Their silence doesn't disprove their existence. It simply reminds us that the most important chapters of human history might be the ones we haven't yet learned to read. The ice finally broke, the waters rose, and in that great drowning, something else was born. In the highlands where refugees gathered, in the river valleys where displaced communities learned to farm, in the stone circles where survivors preserved their most sacred knowledge, the foundations of everything we call civilization were being laid by people whose names we'll never know. Their legacy isn't written in monuments that survived the floods. It's written in the myths we still tell about islands that sink beneath the waves, in the technologies that appeared seemingly from nowhere, and in the persistent human certainty that we've been here before, building, losing, and building again. The waters keep their secrets, but the stories refuse to stay buried. When the rising waters claimed the last coastal plains, humanity didn't vanish into the depths. They retreated to higher ground, carrying with them memories of a drowned world that would echo through the ages. Each step away from the submerged lowlands was a farewell to everything familiar. The fertile fields where communities had gathered wild grains were now beneath the waves. The sacred groves where ceremonies had been held for generations lay silent under fathoms of salt water. The trade routes that had connected scattered settlements were cut by an ocean that showed no signs of receding. The survivors found themselves in a transformed landscape with few of the resources that had sustained their ancestors. Yet from this devastation, something unprecedented began to emerge. As the Younger Dryas finally ended and the Holocene period began, archaeological evidence reveals a remarkable burst of human innovation and social complexity. The timing is too precise to be coincidental. The very moment when the last ice sheets retreated and the flooded world stabilized, human societies began experimenting with technologies and social structures that would become the foundation of everything we call civilization. In the immediate aftermath of the most devastating climate catastrophe in recent human history, survivors didn't just focus on basic survival. They organized themselves into work groups capable of quarrying, transporting, and precisely positioning stones that required sophisticated knowledge of engineering and logistics. They developed artistic traditions complex enough to produce the elaborate carvings that covered every surface. They established social hierarchies capable of directing large-scale construction projects over multiple generations. The level of organization probably came from civilizations that had been destroyed by previous natural disasters. In the Fertile Crescent, wild varieties of wheat, barley, and other grasses began showing signs of deliberate cultivation and selective breeding. Within a few centuries, these plants had been transformed into the domesticated crops that would support the first permanent settlements, and eventually the world's earliest cities. The speed of this agricultural revolution has always puzzled researchers. Traditional theories suggest that farming developed gradually over thousands of years as hunter-gatherers slowly learned to manipulate wild plants. But the evidence from the post-Younger Dryas period shows a much more rapid transformation, as if the techniques of cultivation were being remembered and refined rather than discovered from scratch. This pattern repeats across multiple domains of human activity. Permanent settlements began appearing with remarkable speed and sophistication once the climate stabilized. Astronomical knowledge that required generations of careful observation suddenly appeared in the architectural alignments of early temples and monuments. Rather than gradual invention, this looks like rapid reconstruction, the work of survivors who carried fragments of older knowledge through the long winter and were finally able to implement them again once conditions permitted. The mythological traditions that emerged from this period support this interpretation. Cultures around the world preserve stories of divine beings or culture heroes who taught humanity the fundamental skills of civilization, agriculture, construction, astronomy, and social organization. These figures are consistently described not as gods in the abstract sense, but as teachers who appeared at crucial moments to guide human development. Perhaps these divine teachers were not supernatural beings, but the cultural memory of actual people, the survivors who had preserved crucial knowledge through the catastrophic period and passed it on to communities struggling to rebuild in the aftermath. The mythology transforms historical figures into eternal archetypes, but the core message remains. Civilization didn't develop spontaneously, but was taught by those who remembered older ways. Picture one of these teaching moments. a small group of survivors gathered around a fire in the highlands, sharing the last handful of grain seeds they had managed to salvage from the drowned lowlands. An elder, who remembered the old cultivation techniques, explains how to prepare the soil, when to plant, how to recognize the signs of healthy growth. The younger members of the group, born during the harsh years of wandering, listen carefully to descriptions of fields and harvests they've never seen. When spring comes, they clear a small plot of land and plant the precious seeds according to the elders' instructions. When the first green shoots appear, they're not just growing food. They're re-establishing humanity's partnership with the earth, recreating the agricultural foundation that had supported their ancestors' more complex societies. From such humble beginnings, the entire structure of Neolithic civilization began to emerge. Permanent settlements replaced nomadic camps, surplus food production allowed for occupational specialization, trade networks developed to exchange goods and knowledge between distant communities. Social hierarchies emerged to organize increasingly complex cooperative activities. But the survivors who initiated this transformation carried more than just practical knowledge. They also carried trauma, the deep cultural memory of loss, destruction, and the fragility of all human achievements. This dual inheritance of knowledge and catastrophe shaped the emerging civilizations in profound ways. The monuments they built weren't just displays of wealth or power. They were attempts to create permanence in a world that had proved devastatingly impermanent. The religious traditions they developed weren't just spiritual exercises, they were systems for preserving and transmitting crucial knowledge across generations. The social structures they established weren't just practical arrangements, they were insurance policies against the kind of societal collapse that had nearly destroyed humanity during the long winter. Evidence of this catastrophe consciousness appears in the earliest religious and mythological traditions of every major civilization, prophecies of cycles of creation and destruction that repeat throughout cosmic history, rituals designed to appease forces capable of ending human society, calendar systems that track not just seasons but vast cosmic cycles that bring both prosperity and catastrophe. These aren't abstract philosophical concepts. They're the cultural DNA of societies founded by survivors who had witnessed the end of their world and were determined to prepare future generations for the possibility that it could happen again. The survivors who changed the world weren't heroes in the conventional sense. They were refugees, trauma victims, and displaced populations struggling to make sense of catastrophic loss. But they were also carriers of something invaluable, the knowledge, skills, and cultural memory that represented humanity's first attempts at complex civilization. Their greatest achievement wasn't any single invention or monument, but the simple fact of continuity. They refused to let the devastating interruption of the Younger Dryas become a permanent ending. Instead, they transformed it into a beginning, the foundation story of the world we know today. In doing so, they established a pattern that has defined human civilization ever since, the cycle of growth, catastrophe, survival, and renewal. Every major civilization has experienced this pattern. Every recovery from collapse has relied on survivors who preserved fragments of older knowledge and used them to build something new. Stone blocks hidden deep in a barren hill in rural Turkey are a testament to the preservation of the last memories of an ancient civilization. When archaeologists began digging into the dry soil of Göbekli Tepe in the 1990s, they found a ring of pillars, T-shaped, towering 15 feet into the air, each one carved from single blocks of limestone weighing several tons, and not just randomly placed, arranged in perfect circles, aligned with astronomical precision, and etched with symbols that no one alive today can fully explain. The oldest part of this site has been radiocarbon dated to around 9,600 BCE, That's more than 11,000 years ago, making it older than pottery, older than writing, older than agriculture itself, which means someone at the very end of the Younger Dryas quarried these massive stones, transported them across difficult terrain, and stood them upright in complex geometric patterns, all without the supposed benefits of farming, metal tools, or permanent settlements. But there was no one lived at Göbekli Tepe. Despite decades of excavation, archaeologists have found no signs of permanent habitation, no houses or storage areas, no burials or cemeteries, no evidence of the domestic activities that mark every other ancient settlement. Just these great stone enclosures rising from bedrock like frozen prayers, arranged as if for massive gatherings, but of whom? And for what purpose? Each pillar is covered in intricate carvings that seem to tell a story we can no longer read. Animals emerge from the stone with startling realism. Foxes with bushy tails, wild boars with prominent tusks, scorpions with curved stingers, vultures with outstretched wings, snakes coiled and ready to strike. Abstract symbols appear alongside them, crescents, H-shapes, circles pierced by lines, geometric patterns that repeat across the site with mathematical precision. There's no inscription, no written language we can decipher, but the symbols repeat not just across Göbekli Tepe, but across other newly discovered sites in the same region, as if they're part of a visual code, a symbolic language whose meaning died with its creators. Some researchers suggest these carvings represent astronomical observations, a frozen sky map carved in stone to track celestial movements. Others believe they're mythological, depicting a cosmology and creation story that predates all known religions. There are even those who think Göbekli Tepe preserves the memory of a catastrophic event. But here's the most unsettling part of the Göbekli Tepe mystery. After building and using it for perhaps a few centuries, the people who created this extraordinary site didn't abandon it. They didn't let it crumble into ruins like countless other ancient structures. They buried it. Deliberately and methodically, they filled in the spaces between the pillars with tons of stone and debris, sealing the enclosures beneath a man-made hill layer by careful layer. This wasn't destruction, it was preservation. As if they wanted it to survive the ages, just not be seen. As if they were protecting it from something or saving it for someone who would come later. The question that emerges from this recognition is both humbling and urgent. If the Younger Dryas really did erase an earlier attempt at human civilization, then we are not the first complex society our species has built. We are the latest in a series, and if the pattern holds true, we may not be the last. Beneath the summer sun in Greenland, massive ice sheets crack like breaking glass. Rivers of meltwater cascade toward the ocean in thundering silver waterfalls that can be heard from miles away. The sound echoes across 12,000 years, carrying the same rhythm that marked the end of the Younger Dryas, except this time there's no 1,000-year winter to follow. This time there's only us watching it happen. The Younger Dryas taught a terrifying lesson about how quickly the familiar world can disappear. Within decades, a stable climate system that had persisted for millennia could reverse completely, plunging entire continents back into Ice Age conditions. The mechanism was elegantly simple: disrupt one key system, ocean circulation, and the resulting cascade could lock the planet into an altered state for over 1,000 years. Today, the same systems that failed during the Younger Dryas are showing signs of stress. The Atlantic circulation that shut down 12,900 years ago is weakening again. Recent scientific studies warn that the AMOC could collapse within this century, potentially triggering rapid climate shifts across the northern hemisphere. The difference is that this time we can see it coming, Current sea level rise may seem gradual at 3 to 4 millimeters per year, but it's already displacing millions of people and threatening hundreds of coastal cities. During meltwater pulse 1b at the end of the Younger Dryas, sea levels rose at 40 to 100 millimeters per year, 10 to 20 times faster than today's rate. If that scale of change occurred again, the maps our grandchildren inherit would be unrecognizable. The parallels are unsettling: ice sheets collapsing, ocean currents slowing, sea levels rising, extreme weather events becoming more frequent and more severe. The mechanisms that triggered the Younger Dryas are stirring again, but this time they're driven by human activity rather than natural cycles. Yet there's a crucial difference between our situation and that of the people who lived through the original catastrophe. The survivors of the Younger Dryas had no choice but to endure whatever changes the planet imposed on them. They couldn't prevent the ice dams from failing or the ocean circulation from stopping. They could only adapt, preserve what knowledge they could, and rebuild when conditions finally improved. We have a different kind of choice. We possess scientific understanding that allows us to recognize the warning signs. We have technologies that could, in principle, address some of the root causes. We have global communication systems that could coordinate responses across continents. Most importantly, we have the historical perspective that comes from studying previous climate catastrophes. The question is whether we'll use these advantages or repeat the pattern that has defined human history: growth, overreach, collapse, and painful recovery. The survivors who rebuilt civilization after the Younger Dryas created monuments, agricultural systems, and cultural traditions that lasted for millennia. But they also carried forward a deep awareness of how fragile human achievements could be. Their flood myths, their cyclical calendars, their preparations for future disasters, all reflected the understanding that what had happened before could happen again. Perhaps every civilization contains the seeds of its own transformation. The very success that allows a society to grow and prosper may also make it vulnerable to the kinds of disruptions that periodically reset human development. The Younger Dryas survivors experienced this pattern firsthand. Their ancestors' achievements were swept away by forces beyond anyone's control, leaving only fragments to guide the rebuilding process. Today's coastal cities gleam in the sunlight, their glass towers reflecting the endless dance of light on water. From New York to Shanghai, from London to Miami, these urban centers represent the pinnacle of human engineering and organization. They're magnificent achievements, and they're also extraordinarily vulnerable to the kind of sea level changes that occurred routinely during past climate transitions. A few meters of sea level rise would flood the ground floors of Manhattan skyscrapers. 10 meters would submerge entire districts. 20 meters, the scale of change that occurred during the transition out of the last ice age, would transform these cities into underwater ruins, archaeological puzzles for future civilizations to decode. The Younger Dryas reminds us that dramatic change doesn't require cosmic catastrophes or supernatural intervention. The normal operation of Earth's climate system, when pushed past certain thresholds, can produce transformations that seem impossible from our limited human perspective. Ice sheets that appeared permanent can collapse within decades. Ocean currents that seemed eternal can shut down within years. Coastlines that defined entire civilizations can disappear beneath the waves. But the story of the Younger Dryas also offers a more hopeful message. Human societies can survive dramatic environmental changes if they preserve essential knowledge, maintain social bonds, and adapt to new conditions. The people who lived through the 1,000-year winter didn't just endure. They used the experience to build something better when the opportunity arose. Their resilience came from understanding that change, even catastrophic change, is temporary. The floods recede, the ice eventually melts, the climate eventually stabilizes. What matters is whether enough knowledge and social structure survives the transition to support recovery when conditions improve. Whether we face our own version of the Younger Dryas or manage to avoid it entirely, the basic challenge remains the same. How do we balance the pursuit of progress with the need for long-term sustainability? How do we grow without triggering the feedback loops that have periodically reset human civilization throughout history? The sound of water cascading from melting glaciers carries both warning and promise. It reminds us that we live on a dynamic planet where dramatic change is not just possible but inevitable. It also reminds us that previous generations have faced similar challenges and found ways to preserve what mattered most through even the darkest periods. A single drop of meltwater falls from the Greenland ice sheet into the North Atlantic, joining billions of others in the same journey. Each drop carries memories of winters and summers stretching back thousands of years. Together they're writing the next chapter of Earth's climate story. The question that remains, quiet as wind across the ice, is where we stand in the great cycle of growth and renewal that has defined human history. Are we witnessing the dawn of a new era of wisdom and sustainability, or are we approaching another twilight that will require our descendants to rebuild from whatever fragments we leave behind? The Younger Dryas isn't just history, it's prophecy, a glimpse of what's possible when planetary systems shift beyond the boundaries that define our familiar world. Whether that prophecy becomes our future depends on choices we're making right now, in cities that reflect the light on a planet where the ice never stops listening to the changing sky.